from the disposal of household waste to the disposal of non-toxic industrial and construction waste. Landfills, or dump sites, play a pivotal role in our modern societies. Like any other civil infrastructure, modern landfills require meticulous planning, design, and construction execution with lifetime monitoring during usage and closure. My name is Chido Chache. I talk about geotechnical engineering related topics, including but not limited to construction methods, disasters, and past, present, and future innovations in ground engineering. Please like and subscribe to the channel. With that, let's dive into the video and talk about the geotechnics of landfills. Welcome to Geotechs with Clemens. First and foremost, in order to design for the local and global geotechnical stability of landfills, it is important to understand the mechanical behavior of waste material, the subgrade soil at the landfill site, the fluids, gas, and the interaction of these components. The soil's mechanical behavior can easily be modeled because of its relative homogeneity in relation to that of waste material. On the contrary, it is rather difficult to model waste mechanical behavior. You see, unlike soil, the waste matrix is comprised of different constituents of different individual properties. Remember, municipal solid waste is a collection of household garbage, construction waste, and non-toxic industrial waste. For example, the decomposition of organic materials has an adverse effect on the stability of the landfills. When organic matter decomposes, water and gas are released as a byproduct of the process. This process is neither linear with time nor constant across all different organic materials. This means it is difficult to accurately predict the long-term mechanical behavior like settlement and shear strength with the same ease that we can predict that of soil. The geotechnical aspects of the landfills are also designed with the local weather in mind. The rain patterns and the volumes are included in the design aspects. This is because the fluid from the biodegradation of organic content and that of the infiltrating rainwater creates a toxic leachate, popularly known as the garbage juice. If the leachate is poorly monitored and controlled, it might have disastrous consequences. In the process of anaerobic biodegradation of the organic waste, landfill biogas is produced. The landfill gas mainly consists of methane and carbon dioxide, both greenhouse gases contributing to climate change. Not only is leachate and biogas detrimental to the environment, but it also raises landfill stability problems. A good example, but a tragic event to use as a demonstration, is the Bandung, Indonesia landfill avalanche. In the previous 3 days leading to the 21st of February 2005, the region of Bandung experienced torrential rainfall. In the early hours of the 21st, the residents around the landfill site had 3 almost simultaneous explosion-like sounds a few minutes before the slide. The back analysis of the slide showed that the explosion was due to a sudden biogas release and the heavy rainfall that increased the weight of the waste and poor water pressure were the 2 main triggering factors of the failure. So, the question is, how are modern landfills constructed to deal with the environmental and the geotechnical aspects? Site selection of the landfill construction is critical. The site should have stable subsurface soil conditions, and the groundwater table should be deep enough not to interact with the landfill to avoid contamination. This is one of the reasons why landfills are usually located on high ground. When excavating the landfill pit, the sites are in a slope, and the depth is usually below 8 meters. This increases the local stability and does not require support such as deep excavation projects like those for underground tunnels and tall buildings. Once the excavation has been completed, a liner system is installed. Modern landfills are constructed using a double liner system installed at the bottom and the sides of the excavation. The double liner system is comprised of different materials layered on top of each other, creating a watertight barrier that can prevent leachate from leaking into the ground. The secondary liner is a 2 feet thick leveled layer of highly compacted clay covered by an impermeable geosynthetic clay liner. These standards vary depending on the type and location of the landfill, but generally they require the compacted clay to be at least 2 feet thick, have a minimum density of 95% of the standard Proctor maximum density, having a moisture content within 2% of the optimal moisture content, and having a hydraulic conductivity of less than 10 to the power minus 7 centimeters per second. The geosynthetic clay liner placed on top of the compacted clay is a relatively thin layer of processed clay, typically bentonite, either bonded to the geomembrane or fixed between two sheets of geotextile. The liner acts as the protective cover to the subgrade clay from erosion, and the technology offers some unique advantages over conventional bottom liners and covers. Bentonite is an extremely absorbent granular clay formed from volcanic ash which attracts positively charged water particles. Thus, it rapidly hydrates when exposed to liquid. This bentonite solution is widely used in pile drilling and diaphragm wall excavation to temporarily support the wall from caving in and preventing groundwater ingression before the concrete is poured. In geosynthetic liners, however, as the clay hydrates when in contact with leachate, it swells, giving it the ability to self-repair breaks or any cracks in the liner. To protect the geosynthetic clay liner from wear and tear, an impermeable 60 mm flexible liner is installed. The composite of the two is 1,000 times more resistant to leakage than either components used alone. As I discussed earlier, one of the critical elements in landfill operation and management is the control and removal of leachate. A geocomposite layer used to create drainage systems for various applications such as in highway pavements, foundations, or tunnels is the first element in the primary liner in landfills. It consists of a plastic net core that is sandwiched between two geotextiles or between a geotextile and a geomembrane. The geotextile provides a filter function, allowing water or gas to pass into the net core while preventing soil particles from clogging it. The core collects and transports the leachate to a collection point. To complete the leachate collection system in the primary liner, a network of perforated PVC pipes is sandwiched between a layer of gravel and sand. The sand and gravel acts as a filter separating large garbage materials while this allowing leachate to pass. You see, some of the waste constituents are sharp objects such as disposed construction materials like glass, concrete, and rebar. Therefore, the layer is also a protective shield that cushions the geosynthetics and membranes in the liner system from damage. The leachate collection pipes are also placed at regular intervals across the landfill base with an adequate connection to the geocomposite drainage layer. The combination of pipes and geocomposite drainage layer provide high volume flow paths for the leachate, which reduces the pore pressure and increasing the stability of the landfill. The waste body is divided into individual cells. Waste without bulk components is placed first, which is called the fluff layer. The waste is placed in layers, with each layer being compacted to reduce its volume and increase its stability. A daily soil cover is placed at the working face at the end of each day to minimize odors, pests, and rodents. It also prevents waste from being blown out of the cell and reduces the amount of water that enters the cell. This reduces the amount of water that comes in contact with the waste and reduces leachate production. When the design cell is filled, it is covered and the work is moved to the next cell. A series of wells and horizontal trenches equipped with perforated PVC pipes are placed in a regular interval based on the design criteria to capture the biogas and transport it to a central treatment facility. In traditional landfill structures, the biogas is treated by combustion using flares, incinerators, boilers, gas turbines, or internal combustion engines. These devices can also generate heat and electricity from the biogas, which can be used for various purposes. For sustainability purposes, the biogas can also be used to treat the leachate collected from the landfill. You've been watching Geotechs with Clemens. Please like the video and subscribe to the channel. You can also go and check out my previous video on the ground freezing technique.